Good morning, everyone. Thank you for being here today. My name is Gimhan Nipan Hetiarachi, a software engineering final year student at University of Westminster, and I'm here to present my project titled Graph-Based System for Phytochemical Research in Drug Development. Let's move on. Here is my contents, and the first one is the introduction. So, I'm addressing is the lack of a structured approach for organizing and analyzing medicinal plant data. Currently, data on plant-based antioxidant and anti-cancer properties is fragmented across multiple sources and it making data retrieval and analysis inefficient. So the traditional databases struggle to model the complex interaction between plant chemicals and their medicinal properties. To address this, my project aims to develop a graph based web platform that enables researchers to efficiently search, filter, and analyze plant phytochemical data using a Neo4j graph database. So, let me walk you through the core of the project, the system architecture, and the progress made so far. Let's move on. Here is my project core. So, the project core of this project revolves around three key elements: the problem, the aim, and the objective. So, my research problem is the lack of the structured approach for organizing and analyzing medicinal plant data and making it difficult to explore phytochemical relationships for the researchers and the scientists. And the aim is to develop plant bio, a graph-based system that centralizes medicinal plant data to improve the search, visualization, and analysis of plant phytochemical relationships for this drug discovery. And the objective is to develop a graph database for modeling relationships between medicinal plants, phytochemicals, and their properties with features like search, filtering, and data visualization. So, this project is designed to provide researchers with a powerful tool accelerate drug discovery research. Let's move on. And here is my system architecture diagram. So, let's uh, dive into the system architecture. So the plant bio system implements a robust three-tier architecture that elegantly separate user interface, business logic, and the data storage. So this modern design approach ensures scalability, maintainability, and seamless user experience across platforms. So the presentation tier, the first one, so this tier serves as our user interface layer. Built using modern front-end technologies, this client application runs across multiple platforms and browsers, supporting Windows, Mac OS, and Linux, and the researchers can access the system through Chrome, Firefox, Safari, or Edge browsers. So the front end provides essential features including user authentication, uh, advanced search capabilities, and sophisticated data visualization tools. Uh, a well structured client side architecture manages user interaction through dedicated controllers uh, and maintains clean data management through the client model. Uh, Moving on, at the core of the system lies the application tier. So, powered by a Python, which is Python web framework, a Flask framework, ideal for building robust APIs. So this server layer process requests from the front end and implements our core business logic. It includes specialized components for managing plant models, compound relationships, and data processing. Communication between front end and back end is handled through standardized HTTP protocols and also a custom DC bus connectors, ensuring reliable and efficient data exchange. So, moving on, next tier is the storage tier. So, the storage tier completes our architecture with a Neo4j graph database. So specifically chosen for its exceptional capability in handling complex plant compound relationships. And also these graph databases excel at managing highly interconnected data and making them perfect for biological relationship mapping. uh, Also, this tier efficiently stores and manage the relationships between plant and compound, enabling sophisticated queries and comprehensive data analysis. So overall, this architecture demonstrates careful consideration of modern software design principles. So, and by maintaining clear boundaries between layers while ensuring seamless integration, the plant bio platform achieves both technical sophistication and practical usability. So the system design not only support current requirements but also provide flexibility for future enhancement and scaling needs. Let's move on. And as you see, the system is divided into three main components: the front end, the back end, and the database. So let's talk about the front end. So the front end is built using HTML, CSS, and the JavaScript, and which are core web technologies for structuring, styling, and adding interactivity to the platform. And this ensures a clean and user-friendly interface for the researchers. Moving on to the system architecture explanation. Next one is the backend. So the backend is powered by Flask, a lightweight and flexible Python web framework. So Flask handle API requests, uh, server-side logic, and the communication with the database, and it also implements RESTful APIs for the efficient data exchange between the front end and the back end. And the databases. So the databases is built using Neo4j, which is a graph database specifically chosen for its ability to model and query complex relationships between plants, compounds, and their properties. So this enables efficient storage and retrieval of interconnected data, which is critical for drug discovery research. So let's talk about why is this tag? Why I'm using this tag? Uh, One of the reasons are simplicity, which is the Flask provide a straightforward way to build server-side APIs, and Neo4j graph-based structure simplifies the modeling of complex relationships. And the next reason is scalability. Both Flask and Neo4j are lightweight and scalable, and making them ideal for handling growing datasets and user traffic. And also, my next reason is ease of the development. So Flask is beginner friendly and has extensive community support, speeding up the development. So this architecture has ensured that the system is both powerful and easy to use. Let's move on. Uh, Identification of project stakeholders, and I used an diagram. So let's check a key stakeholders involved in this project. So using an onion diagram, I have categorized them into the three layers. So the core system, as you know, the plant by web application itself. And the next layer is the direct stakeholders. These include researchers, scientists, and who will use the platform to search, filter, and analyze the data. And the next layer is the indirect stakeholders. Uh, this includes domain experts, research advisors, and traditional medicine practitioners who provide valuable input and validation for the data. And the last layer, which is the external influences. So these include the competitors and the medicinal plant research communities who ensure the system meets regulatory standards and align with broader research goals. So each stakeholder group has played uh, a role in shaping the development of this project. So I have created a table uh, like this: the stakeholders group, then the every stakeholder in here and their role and their each influence on the project and the importance for my project. So this is easy to review and realize about the identification of my project stakeholders and their influence on this project. So let's move on. Uh, Now discuss about the formal requirements for this project. So first one is the functional requirements. So the functional requirements defined what the system should do to meet the needs of its users. So these requirements are directly tied to the core functionalities of the platform. And the next one is the search functionality, which means the users should be able to search for plants and phytochemicals by name, properties, or other relevant criteria. So this feature has been completed and allows researchers to quickly retrieve specific data from the database. And the next one is filtering, which is users should be able to filter data based on antioxidant properties, anti-cancer properties, and uh, geographic region. And this functionality has been completed, enabling researchers to narrow down their search results based on specific criteria. And the use authentication. This system includes a use authentication feature allowing users to register, login, and access personalized features. So this has been partially completed and ensures secure access to the platform. And the data visualization, users should be able to visualize chemical structures and the other relevant data in interactive manner. So this feature is currently in progress and will allow researchers to explore data more effectively once implemented. And let's talk about non-functional requirements. So non-functional requirements defines how the system uh, should perform and the quality attribute it must process. So scalability, the system should handle increasing data volumes and user traffic efficiently. So this is in progress as in the system is being tested with larger dataset to ensure it can scale effectively. And the next one is security. User authentication has been implemented and ensure secure access to the platform. And this document has been partially completed with password encrypted using secure hashing algorithms. And the performance, the system should provide fast response times for all user interaction with queries returning results in less than 2 seconds. So this is in progress as the system is being optimized for speed. And the next one is usability. The system should have an intuitive and user-friendly interface. This has been completed uh, with a clean and responsive design that ensure ease of use for researchers. And the last one is comprehensiveness of the ontology, which means the system should truly represent the relationships between plants, chemicals, and their properties. So this is in progress as the ontology is being refined to ensure it accurately models complex relationships. So these requirements ensure that the system is functional, scalable, and user-friendly. And also here you can see the implementation status. Let's talk about that. So the implementation status provide an overview of what has been completed, what is in progress, and what is still pending. So completed, which means the search and filtering functionality as well as user authentication have been partially completed and did some testing, and these features are now operational and not much allow users to efficiently retrieve and filter data. And in progress, which means data visualization in currently being developed. This feature will enable users to interactively explore chemical structures and other data, enhancing the platform usability. So the pending is the final UI enhancement and the testing and are still pending. So these tasks will ensure the platform is polished, user-friendly, and free of bugs before the system deployment. And the project is on track as of as. And the next step is involve completing the data visualization features and conducting final testing. So move on. I have created the use case diagram using the functional requirements on the system. So these are the functions which the directory stakeholders can use. Those are the applications, search and filter the plant data and visualize. The scientists and researchers both can do it. Apart from that, the only scientist can upload the data for the system. So let's move on. Next one is the updated time schedule. So let's take a look at the updated time schedule since the project proposal and requirement specification. The PPRS significant since that PPRS significant progress has been made, including refining project requirements, updating the system architecture, and the developing a working prototype. So the timeline has been adjusted to accommodate the development of data visualization features and final testing. So the project is on track to meet its deadlines. So I have adding a status column here to review and realize easily which is done, which is in progress, and which is pending. So let's move on to the conclusion, wrap up my presentation. So in conclusion, this project aims to develop a comprehensive web-based platform using Neo4j to model and analyze the relationships between medicinal plants, phytochemicals, and their properties. By focusing on efficient search and filtering functionalities, the platform will provide researchers with a valuable tool for retrieving relevant data, thereby supporting advancement in cancer drugs research, not only the cancer, in drug discovery field. So as we progress with data visualization features and final testing, the project is on track to offer a scalable, user-friendly, and reliable solution for the scientific community. So here are my references which I used, and thank you for your attention.